As we start, we want to prove this theorem that's on the board. This question paper, because obviously we're keen to know when these papers were written. This one is a very good paper written in the year 2017 by the IEB students. Right, question 5, obviously it's the beginning of Euclidean geometry, and we can see that we need to just recap on the proofs, or it's something very straightforward. But we begin on a lighter note. To prove the theorem that states the angle between a tangent and a chord is equal to the angle in the alternate segment. And so we spoke about this theorem here. So, right, so here is the statement, part of the proof. We need to write our answer here. And right, this is the answer book. Right, given DE, given that DE is a tangent to circle center at A, okay, so DE is a tangent at A, B and C are points on the circle. So you can see that B and C are points on the circle. Right, what are we required to prove? Okay, so we need to put here, we're required to prove R. So it's therefore important to note that um, we need to indicate exactly what we need to prove. So at this point, what do we need to prove? There are two ways in which we can state that. Either we prove that this angle here equals angle B, or this angle here equals angle C. So there are just basically two ways to actually state this one. So we can just state one of them. So we're going to just prove that angle, for instance, CAE is equal to angle B. Okay. Okay, that's fine. Right. So how do we prove that? We state that. So we decide to prove this angle here is equals to angle B. So we shall prove that, we shall decide to prove that CAE is equal to angle B. In other words, we have that angle CAE, right? Angle CAE is equal to angle ABC. Okay, that is what we are deciding to prove. This angle here is equal to that angle there. How do we prove that? So we need to perform a construction. Right, so how do we perform the construction? So if you want to prove that this angle equals angle B, you construct a diameter of this circle quickly. Okay, this is obviously bookwork. And now, because you want to prove about angle B, you go to the other angle. Your construction must go to the other angle because you want to prove about angle B, so you go to C. This diameter obviously is a chord that passes through the center of the circle. Next, right, what are we supposed to prove here? So in other words, you construct, right, construction, you indicate obviously that you draw a diameter, okay, so you need to label this point and give it a name. We can give this one F, and this one is C, right? So you draw a diameter that joins AF. Full stop. Right. Moreover, you then join FC. You join FC like that. Okay, you join FC. FC. Right. So let's start the proof. Let's begin the proof. Right. So the proof right now, we have this diagram here. How do we start the proof now? We can see clearly that at this point, we have that the angle OAC plus the angle CAE is equal to 90 degrees. So we prove that we say this angle here which is OAC plus CAE. This plus this is 90 degrees. That is the first thing, because this is a tangent and this is a diameter, so the tangent is perpendicular to the line through the center. Right, so this is what we say. So we're gonna say OAC, how we write it, we add, so OAC is this angle here plus this one here, which is CAE, right, plus CAE, and this result is equal to 90 degrees. Why is it equal to 90 degrees? There must be a reason for that. The reason is because you have a tangent that is perpendicular to a diameter. A tangent is always perpendicular to a diameter. Right. So obviously it makes sense, therefore, to say this angle here is 90 degrees here. But also it makes sense to realize that this is the diameter, and therefore it subtends an angle of 90 degrees at the circumference of the circle. And this means that we can see that FCA is equal to 90 degrees. Right, so we have that FCA is equal to 90 degrees. Right, so in other words, so this angle here at circumference obtained by the diameter is 90 degrees. Why is that the case? Because it is an angle in semicircle. The diameter cuts a circle into two equal parts, such that we have a semicircle on one side. Semi means half circle, half circle. So right, so a diameter subtends an angle of circumference. We can say angle subtended by diameter, or we can say it is an angle in semicircle, or it is an angle in half circle. We use the word semicircle. Right, so we're good now. And what is the meaning of these? So we also note, therefore, that angle OFC plus angle OAC equals 90 degrees. So also, because this is 90 degrees, when we add these two angles, we must get 90 because they're angles in a triangle must give 180 degrees. So we're going to say OFC plus OAC is 90 degrees. OFC, right, OFC plus OAC, right, equals 90 degrees. Right, we continue quickly. We continue quickly. Right, so what did we do now? What do we do now? What do we do now? Okay, I was saying that obviously this is true because of the angles in a triangle. Right, so this is the case because of angles, right, angles in triangle. Angles in triangle, because now we can see that if we add this plus this, we get exactly 90 degrees, because this one is already 90 degrees. Right, now we make the comparison to say, therefore, what conclusion do we draw out of these now? Because we can see, therefore, that this, that, and that are all 90 degrees. We have like 3 90s here in a sequence. But now, if we look very carefully, the first two equations are able to, they have OAC and they have OAC. We don't have a lot of time in the metric exams. A small observation like this is enough to say these are both equal to 90 degrees. And therefore, if we make them equal, we equate them, OAC is going to cancel. And that means that we have OFC is equal to CAE. Right, so OFC is CAE. Just comparing the first and the third equations, because they're both equal to 90 degrees. Okay, but what else do we observe here? What else do we observe here? Okay, but we have that OFC, look at this. But we have that OFC is actually equal to ABC. Okay, this angle is equal to this one. This angle is equal to this one. So OFC is equal to ABC because they're angles in same segment. That's what I'm going to write down here. But OFC is equal to ABC because these are angles in same segment. They're angles in same segment. Okay. Therefore, thus we're able to make the observation that OFC is CAE, but OFC is ABC. It means, therefore, that CAE is equal to ABC. Okay, because these are both equal to OFC, so it means that CAE is equal to ABC because this equals OFC. Okay. And this is exactly what we wanted to prove. Because we said we want to prove that CAE is equal to ABC, and we've proven that CAE is equal to ABC. It's exactly what we said we are required to prove, and therefore we are done. Okay, so that is therefore one thing. So we learn how to write the answers in the matric exams. This is extremely important for us to learn how to write down the answers. Okay, so we are actually in business and we continue right now to look at the next question. And now this is the theorem called the 10-chord theorem. We've just written a very detailed proof to it in this past exam paper of 2017. Next question. Right, next question is this one. I gave this one as a homework. I gave to you guys, I gave this to Marang, I gave this one to Ayanda, I gave this one to everybody, at least who is expected to be here this afternoon, with the exception of those who actually maybe are not able to join us now. So it is okay that, yeah, okay, in the diagram below, two circles are drawn intersecting at B and F. Here are the two circles. They actually intersected B and F. F is a tangent to the smaller circle at F. Right, you have that actually CF is a tangent to the smaller circle at F. Okay, so in other words, CF is a tangent. Note that. A and G are points on the circumference of the smaller circle. A and G, here they are points on the circumference of the smaller circle. Chords FC and BD of the larger circle intersect at E. Okay, so FC and BD are chords, and therefore they're straight line segments, right? So if you look at actually your FC and your BD, they are therefore chords, and chords refers to straight line segments because they intersect at the point E, and therefore they don't actually bend at the point of intersection at the point E. Right, so we have that ABD is a straight line. Okay, let's look at that one. We have ABD, the straight line. Okay, because the examiner is telling us it's a straight line because it might not be straight as it looks. Okay, so in which case, we can have a situation in which it looks straight, but it is not straight. So the examiner is telling us straight away that ABD is actually a straight line. Okay, next, we have that angle C equals 70 degrees. Angle C equals 70 degrees. Angle D is 52 degrees, and they've been given that way. Right, we remember a very important point about the existence of a tangent, where CF is a tangent to the smaller circle at the point F. Okay. CF. Okay, right. So you actually are there. All right. So CF is a tangent to the smaller circle at F. All right. So here is CF. It is a tangent to the smaller circle at the point F. Next question. Determine the size of G1. Where is angle G1? We're interested in finding the size of the angle G1. And here is the angle G1. Right. I gave you this one as a homework. I don't know, obviously, if you guys spent time on it, trying to prove this one. And I know that it is way too easy to prove, but I know that you guys worked on the question throughout the evening, post potential yesterday. I'm going to give also some just short questions today as well at the end of our discussion, to test your understanding on the things we will do today. Okay, right. Anyone, what do you think angle G1 is? Anyone? And why? Did you try this question or maybe not? I don't know. I gave you yesterday evening. Right, I gave you yesterday evening. Okay. It's silence in class. Right. We realize first things first. Okay, thank you so much for having Ayanda back there, because I had lost Ayanda. Right. So if I lose you, always you can notify me. You can just try to actually join back, please, because yeah, it happens. First things first, I want to find the size of G1. Here is G1. We have a couple of observations. We already know that this one is 70 degrees, but we know therefore that this angle of 70 is also B3. Yes, please. Okay, you're here, right? No question.
No, sir.
Okay, thank you. Right. So we know that B3 is also 70 degrees. Why B3 equal to this angle here? Because we know that from grade 11, right? We know this. If we have this thing here, this angle here equals this. Sometimes call this the butterfly. So we have that B3 is equal to 70 degrees. Right, so we have that angle B3 is actually equal to 70 degrees. Why is angle B3 equal to 70 degrees? Because these are angles in the same segment. Angles in same segment. Angles in same sag. Okay, once you say in same sag, we understand in same segment. What is F2? Also, in other words, we can see therefore that this angle here is actually equal to 70 degrees. But we as well are able to note that angle F2 also obeys the angles in the same segment relationship, in which case, therefore, we can see that angle F2 is equal to 52 degrees. So it means that F2 here is equal to 52 degrees. Why is F2 equal to 52 degrees? Because it is F2 is equal to the angle D, and if F2 equals the angle D, they are angles in the same segment as well, like those. So because these points F and D lie on the circumference of the circle. Right, so these are angles in same sag, angles in same sag, angles in same segment. Next. Right, so we have these two here. But we want to find the size of angle G1. So we continue. A couple of observations become very important here. There is another theorem we learn in geometry that says that if you have a circle like this, and you have a quad like this, a quadrilateral like this, and you extend one side of the quad so that it is a straight line, this angle here will always be equal to that angle there. We say the exterior angle of a cyclic quad equals the interior opposite angle. There it is, the exterior angle. And therefore it means that this angle here, which is B3, is equal to G1 and G2. That means G1 and G2 together equal to 70 degrees. We write that one down. Angle G1 plus angle G2 is actually equal to 70 degrees. Why? Because these are actually exterior. We say the exterior angle of a cyclic quad. The exterior angle of cyclic quad equals the interior opposite angle. Full stop. Next. So we have seen, therefore, that G1 and G2 together combined, they equal 70 degrees. We want to find G1. Next, we want to find the angle. Want to find the angle F2. Right, or want to use the angle F2. The angle F2, because this one is a tangent. Remember, this CF is a tangent. So the angle between the tangent to the circle and a chord, it equals the angle subtended by this chord. And this chord subtends angle G2. It means that angle F2 is equal to angle G2 because the angle between a tangent, a circle, and a chord equals the one in the alternate segment. So F2 equals G2. F2 equals G2. And therefore, F2 equals G2 equals 52 degrees. I write that one down. So we write angle F2 is equal to angle G2, which equals 52 degrees. Right, because of the 10 chord. 10 chord theorem. Because of the 10 chord theorem. Okay, now we have this. So F2 equals exactly the angle G2 because of the tangent and the chord. Okay, right. It means that angle G2 already we know that it is equal to 52 degrees as well. As F2 is 52 degrees, and therefore it's obvious to find the angle G1 because already we know that this whole angle is actually equal to 70 degrees. Here, this one is equal to 70 degrees. And therefore, we can be able to see clearly that we just need a little bit here, a portion. When added to this, it gives 70. Or it means it is 18 because 18 plus 52 is 70. So G1 is 18 degrees. G1. G1 is 18 degrees. Okay, G1 is 18 degrees. So angle G1 equals 18 degrees. We're done with this question because they asked us to find the size of the angle G1. And so G1 is equal to 18 degrees. We can come here and realize, therefore, that angle G1 in the diagram equals exactly 18 degrees. So G1 is equal to 18 degrees, and we have been able to determine that angle there. Next question. Right, we look at the next question. Right, we're to spend time on this if need be, but we're looking at possibly geometry at the moment and want to make sure that you have a fair understanding of those. We need to work around the clock to perfect our skill in math. Okay, obviously we understand that. Let's not jump into geometry. Yeah, that is another form of geometry, coordinate geometry. Okay. Right. Okay, here's another nice question. Similarity and proportionality. In the diagram below, a circle passing through A, B, and D is drawn. Any question?
No, sir.
No question. Okay, right. In the diagram below, a circle passing through A, B, and D is drawn. Okay, so we can see the circle passes through A, B, and D, and this circle has been drawn. CD the tangent to the circle at D. Okay, so this CD is a tangent. Right, so the couple of observations that we're going to already make. If it's a tangent, then we know this angle here is equal to that angle there. Okay, so we make that observation. Right, next. Okay, prove that triangle ADC is similar to triangle DBC. Let's see. ADC is actually similar to triangle DBC. Okay. Right. But obviously, we can already see that angle A is equal to angle D, or A is equal to angle D2 because of the 10-chord theorem. Okay, because we're dealing with DBC, but we have also the triangle ABC, in which angle A is part of the triangle ADC. Okay, we start the proof. Right, this is how we begin the proof. Then the proof starts as follows. So we are looking at this question, and this is question 9. We can see that angle A is equal to angle D2. Why is this the case? Because of the 10-chord theorem. Because of the 10-chord theorem. Okay. Next. What next do we have here? Right, so the triangle ADC has the angle C, but also the triangle DBC has the angle C. So in other words, that means that the angle C is a common angle. Or you can indicate already that the angle at this point, you can say, because you're dealing with triangle ADC, right? So you can label these in many ways. So you can say, for instance, it is DCA, right? So you can say DCA is equal to, right? So we're dealing with the angle DCA is equal to the angle DCB, right? It's equal to the angle DCB. Why are these the case? Right, because these are just all describing the same angle C. So Right. In other words, these are equal because the angle C is a common angle. Is a common angle. So obviously we understand at this point that the angle C is actually part of the triangles. Okay, next thing. So we already have two angles. We've already dealt with A, we've dealt with this one, we've dealt with this one. So we're just left with the angle in the triangle. For instance, in the triangle DBC, we're left with the angle B2. In the triangle ADC, we are just left with the whole angle D. And therefore, we infer on the third angles. Right, so we have that. And now we realize that we have the angle here that is left. We have the angle ADC. Right, angle ADC must be the same as. So if you look at the angle ADC, it's equal to the angle B2, equals to the angle B2. Why? Okay, because you can say angles in triangle, right? So, or we say third angle. It's popular to say third angle in triangle. Okay, right. So with that said, if you don't want to say third angle, you can also say angles in triangle. Okay, because the angles in triangle, now when you add them up, when the two are equal, the third angles are as well equal in the respective triangles. And therefore, now you have the angle A here. You have, for instance, moreover, the angle D, and you have the angle C. So the conclusion, therefore, is that for the conclusion follows, therefore, triangle ADC is similar to triangle, right? So we take the ADC, ADC is similar to triangle, right? To triangle DBC. Triangle DBC. Why are these triangles similar? Okay, the reason why they are similar is because of the angle. Right, so we are in business. And therefore, we're just required to prove that the triangle ADC is similar to the triangle DBC. And we have proven that very clearly in a series of clear steps. And the proof is evident, okay, from the diagram given here. Right, and the information given on question 9 in the IB paper 2017. Next question. Okay, this one is very interesting and nice. We need to show that AD times, or rather AB times BC is equal to DC squared minus BC squared. Right, so AD times BC is DC squared minus BC squared. So, let's prove this. Right, so we need to look at where to start with this. In which triangles are we gonna work? It is very clear that you're having lengths like AB. You have BC, which is BC. You have DC, which is DC. You have BC, which is BC. So it relates to these triangles here. So we tell the examiner that we're going to work in these triangles. Right, so in triangles ADC that we've proven, ADC, and triangle, this one, DBC. Okay. In those triangles, we note that triangle ADC is similar to triangle DBC. Why? Because it was proved above. Proved in A above. Okay. Right. We don't need to prove it again. Right. And then it follows what I said yesterday here. What I said yesterday. What did we say yesterday? Yesterday we said that if you have this similarity and these angles are in the right order, A is equal to D, D equals B, C equals C, then we can be able to write the correct ratios. So if this is true, thus, if two triangles are similar, then the corresponding sides are in the same proportion. If the corresponding sides are in the same proportion, it means, therefore, we take the first two over the first two. So we can say AD over DB is equal to the next two, DC over BC. We take the first and the last. AC over DC. Okay, glad that you're able to see that. Okay, obviously I'm going to ask you a couple of questions. We're still discussing. So from the similarity of the triangles, so if two triangles are similar, we say then the corresponding sides are in the same proportion. And this is actually what follows. But we need to choose the right parts of this equation. Which parts are we going to use to prove this? So we need the part that has, for instance, DC. So this part has DC, but also this part has DC. So we shall do this part with DC and this part with DC. We don't, here, there's no AD here, but there's no DB as well. So we're going to take the second and the last. Right, so hence. Right, so hence we have that we can take DC over BC, which is equal to AC over DC. Right. And then with that said, what do we get out of this? You cross multiply and we obtain DC squared. Right, if you cross multiply, it's DC times DC, which is DC squared. It's equal to, all right, you cross multiply these here. And what do they give us this? Right, you can write exactly BC times AC, like this. Okay, we got one equation now. But how far are we from this? Right, so we want to prove that this is the case, but we already have DC squared, so we need to prove something else. We need something else. But what do we know about any of these sides here so that we're able to prove this? Can we be able to get anything else? Yes, we can. Okay, we know about AC from the diagram. Let's look at AC in the diagram. If you look at AC in the diagram, AC is equal to AB plus BC. AC is AB plus BC. So, but, right, but, yeah, but, okay. Hello, my dear. Yes, hello, my dear. Hello, my dear. Yes, please, my dear. No, she went out. All right, that's fine. She went out. She said she was going to zone something. Yeah. Okay. Yeah. Oh, all right, thanks, my dear. All right, fine, thanks, my dear. AC and then is equal to AB plus that. So AC is equal to, but AC is equal to AB plus BC. Okay. Therefore, right, so therefore, we can be able to write the DC squared. So which means that DC squared is equal to, we come here, this one is BC. What is AC? AC is this. So we put AB plus BC. And we multiply everything through. Right, if we multiply everything through, what is this here? Right, so this is actually BC times AB plus BC times BC, which is BC squared. Right, because we have BC times BC, which is BC squared. So how far are we now? We are close because we just have this here and we have just proven this. We have just proven this. So we are glad because now from this equation, we have that D C squared is equal to, right, so you can write it exactly like this. You can write the AB first, right? You can write the AB first. So we have exactly here AB times BC plus BC squared. Right, we transpose things around. If we transpose terms around, we start by writing AB times BC. So we can start by writing here AB times BC, and this is equal to DC squared minus BC squared. So which means that we have this, right? So which means that AB times BC is equal to DC squared minus BC squared. There it is. AB times BC is equal to DC squared minus BC squared. We've proven that. Okay, we've shown a lot of steps here, obviously, but we could shorten these in as much as we possibly can. Right, because it looks a little bit lengthy there, but yeah, it can be shortened. Okay, that is the proof. That is the proof to part B from the similarity of the two triangles ADC and the triangle DBC. Next question. Okay, this video is recorded so you'll play this back. But when you play this back, it's very important that you listen and watch carefully, and then make sure that you write notes. You need to write notes. Notes actually must be written because they help you train your ability to write, and that is what in the test and the exams you need to do. You need to write, and so you need to cultivate that skill. Right here we have circles that touch internally. Right, these two circles touch internally. Right, there are circles that touch externally and there are those that touch internally. In the diagram below, two circles touch internally at A. They touch internally at A. AB is the diameter of the larger circle. Let's look at this very carefully. Right, the examiner is telling us that AB is the diameter of the larger circle. AL is the diameter of the smaller circle. AL is the diameter of the smaller circle. We can see that. S and L are the centers of the circles. S and L are the centers of the circles. There. S is the center of the smaller circle, and L is the center of the bigger circle. Okay, or the larger circle. D is a point on the smaller circle. Where is D? Here it is. Right, so D is a point on the smaller circle, which is on the boundary. And C is a point on the larger circle. So C is a point on the larger circle. Right, ABC is a straight line. AB C is a straight line. Okay, it's very important that this one is a straight line. Right. Very nice question from the IB examiners. Okay, we continue. Right, so M is a point on LB. M is a point on LB. So that MN is parallel to LC. MN is parallel to LC. Okay, these are parallel. Okay. There is something for us to prove. Prove that DL is parallel to CB. Let's look at DL. Prove that DL, right, here is DL is parallel to CB. Okay, we need to prove this. And to prove this is very, very easy. How do we prove this? A couple of observations first to make, because this one is a center. So this one is the diameter. The diameter will always subtend an angle of 90 degrees at circumference. This is also the center. So a line that passes through the center of the circle is called a diameter. A diameter subtends an angle of 90 degrees at the circumference of the circle. So this is also 90 degrees. And therefore, if this 90 and this is 90, these two angles here are corresponding, therefore. Okay, so that this actually is going to be parallel to this, and we're done. But we need to write it down very nicely. But exactly that is what is happening here. Right, so we need to state that ADL is 90 degrees. ADL is equal to 90 degrees, which is an angle in semicircle. Right, we note that actually ADL is equal to 90 degrees. It is an angle in semicircle. Right, but also we can see that ACB. Right, we can see that here ACB is equal to what? Is equal to 90 degrees because it is also an angle in semicircle, or it is an angle subtended by a diameter. So we say ACB equals that. So ACB is equal to 90 degrees. Why is it 90 degrees? Because it is an angle in semicircle. An angle in semicircle. Therefore, right, from which we're able to see, therefore, that DL is parallel to CB. DL is parallel to CB because why is it parallel? We have seen that this angle is 90 degrees and that angle is 90 degrees, and these angles look like corresponding angles because if you remember very well, the corresponding angles are angles in F. If this angle is equal to, normally we say if this is parallel to this, then these angles are equal and they are corresponding. So now at this point, DL is parallel to CB, and with that said, it is the converse. It is the converse. Right, it is the converse of the following statement. That says the corresponding angles are equal. Right, corresponding angles are equal because we have found that these angles are equal, and therefore the lines are parallel. So it is the converse of the usual one, because first we say if the lines are parallel, then the corresponding angles are equal. At this point, we started with the angles. We said the angles are equal. And therefore, if we start with the angles and then end up with parallel lines, we say that we are dealing with the converse of the corresponding angles result. Okay, right. So we have to prove that DL is parallel to CB, and we have that DL is parallel to CB. Okay, so these are past exam questions. They require a little bit of analysis, but I know that they are very, very straightforward. So, but we need to pay specific attention, particular attention. All right. Right. Right, I understand. All right, good. Next question. Okay, there's something for us to prove, something small. We need to prove that twice SD is equal to LC. Twice SD is equal to LC. Twice SD. Twice SD is equal to all right. Twice SD is equal to LC. Okay, let us prove these. But it is very, very obvious. Very, very obvious. Right. What do we prove here? Right. So, right. Obviously, you prove that twice SD is equal to LC. So, this obviously is what we tend to see as the midpoint result, the midpoint theorem. Right, the midpoint theorem. So we use just that one there, okay? So, but we can see that first things first, LC is equals to LA, because this is a radius from the center. L is the center, so it's a radius, and that's the radius. So LC is equal to LA. They are radii of the larger circle. So that's what we say. LC is that. LC is LA. Radii of the larger circle. Right, these are radii of the larger circle. Next. Right, next we make another observation. SD. SD is equal to SL, because also S is the center of the smaller circle. So we can see that SD is equal to SL, because from the center to the circumference is the radius, and also that is also another radius. So SD is SL, these are radii. But okay, SD is equal to SL, is also equal to SA. Radius, radius, radius. This is the center, so you can see every line from the center is the circumference is the radius. So SD is equal to SL. SD is equal to SL is equal to SA. These are the radii. They're the radii of the small circle. They're actually the radii of the small circle. They are radii of the smaller circle. Radii of the smaller circle. Okay. Smaller circle. Okay, next question or next point. we've seen that this guy equals this guy equals that guy. Okay, those are line segments that are equal to each other. But also we know that LA is SA. LA is SA plus SL. Let's go. LA is SA plus SL. So we write that one down. But LA is the same as SA plus SL. Okay? Look at it again. We can see that LA is actually SA plus SL. Therefore, at this point, you have LC is equal to, we are supposed to prove that LC is twice SD. So we have this. LC is LA, but LA is SA plus SL. Right. So at this point, what do we know? So we can therefore see that LC is this one here. LC is equal to what? Is equal to LA. LC is LA, but LA is SA. And SA is what? Is SD. So in the place of SA, we can put SD plus, then you have SL. SL is also SD. Like that. So that LC is equal to, what is SD plus SD? It is twice SD. It is twice SD. So LC is equal to twice SD. And that is what we're supposed to prove, that LC is twice SD, and we've just proven that one for a good 3 marks there. Next question. We need to now determine the value of this for 2 marks. We need to determine the value of SL over AB. SL over AB. How do we do that one? SL over AB. SL over AB. So let's first look at what this means. What is SL? And what is AB? Okay, let's look at this. We're looking at SL over AB. Let's look at the diagram. SL over AB. Okay, they ask you the question in the exam and then you start looking. Here is SL. Here is SL. And yes, my dear. Yeah, what are we sharing upon, you know? Yeah. Zone something, you know? All right. So you have SL. Okay, no, I'm fine, my dear. All right, so you have SL and you have AB. You must deal with SL and over AB, but you can see that SL is just part and the AB now has these other parts here. So from this, we were able to see that At this point, SL is equal to AS because these are radii. SL is equal to AS because these are radii. C. AS is equal to SL because they are radii. Okay, here you are dealing with radii. Next you have AL and LB. Let's look at this now. You have AL and LB. What about AL? Because we must do SL over AB, but in view of AB, we can see that AL is equal to LB. These are also radii. And AL is equal to LB, and these are radii. And this means SL over AB. What is SL here? What is SL? Right. So now SL can be written as what? As AS, for example. Right. So in other words, this one you can write as the AS over. What is AB? AL plus is equal to LB, which means that AB is equal to what? Because this is AB. AL, LB is AB. So in the place of AB, you can put twice AL. Twice AL. AS over. What is AL? Right. AL in terms of AS. It's obvious. AL in terms of AS. AL. Yes, please. We can see that at this point, AL is equal to 2 times AS, because these two things, they give us AL, and these are equal. So which means that AL is 2 times AS. AL is 2 times AS. AL is 2 times AS. So AS cancels, and 2 by 2 is 4. So this is 1/4. And we're done. We're supposed to prove that SL over AB is 1/4. Or we determine the value. And we have determined the ratio. The ratio is actually 1:4 or 1/4. Next question. Right, the examiner decided to give us a couple of things. They decided to give us AB equals 30 units. If AB is 30 units and this is BN over NC is equal to 7 out of 9, then determine the length of LM for a good 3 marks. So let's just get the marks. Okay, at this point, they're telling us that AB is equal to 30 units. But it's like saying we already know much about this diagram. So we know that AL equals LB. So it's like we know AB is 30 units. AB is 30 units. So from which we can be able to get LB. So AB is 30. Implies that what is this one? Is AL plus LB. AL plus LB is 30. That is the meaning, because AB is AL plus LB. And now AL is equal to LB. So this means that you have twice LB is 30. Why is twice LB equals 30? The reason is that LB is equal to AL, radii. Okay, we have seen that already many times in the diagram. So if twice LB is 30, you divide 30 by 2, you get 15. So LB is 15. Okay. And this LB, we've seen that is from the center to the boundary, and therefore it is a radius. Okay, let's take a look. LB. Let's take a look. LB. LB itself is from the center, L, to the circumference, and therefore it's a radius. So it's actually 15 units. Okay. Next question. So we want to find now, but we also know that Bn over Nc, they've given us Bn over Nc equals that. Okay, let's look at this very carefully. Right, let's look at the diagram and look at Bn over Nc in the diagram. Bn over Nc, it's 7 out of 9. Bn over Nc, right, so if you look at these carefully and realize you are looking at Bn over Nc, Bn over Nc, Bn over Nc is equal to Bm over Ml, for example. Bn over Nc is Bm over Ml. Right, so we have that. So if right, so this Bn over Nc is here it is, Bn over Nc has been given. Bn over Nc is 7 out of 9. So Bn over Nc, you can say 7x over 9x, Bn. Right, Bn, it's 7x over 9x. Bn over Nc is 7x over 9x. And then we want to find Lm. Right. So if you want to find Lm, we can be able to find that with ease, because from what we've already got that LB is what? It's 15. So this LB we got at the bottom is 15. We have seen that this one is 15. Right. It's exactly 15. So which means that at this point, we can use the proportionality theorem. The proportionality theorem here will say that if you have these, then you can have LM, according to the proportionality theorem, LM over 15 is going to be the same as Cn over Cb. So that's why LM over 15, the proportionality theorem. Right, so we have LM Right, so we have LM over 15. Hey, look at this very carefully because it's a little bit, you need to remember this. Okay, it is the proportionality theorem we're using because if we're saying LM over 15, it must be equal to Cn over CB. Cn over CB. Right, Cn over CB. Right, so you have Cn over CB. Okay. So which means you have Lm, which is what we want out of 15, is equal to, what is Cn? Right, Cn is like this one. So you can look at it as 9x over CB. What is, that is Cn over CB. Let's look at CB. All right, Cn is 9x and CB is going to be 9x plus 7x, which is 16x for CB, 16x. For CB, we use 16x. Okay, so it is Lm over 15 is 9 out of 16. We are interested in Lm. So it is 9 out of 16 times 15, which is equal to what? Okay, so use a calculator here to get the result. So now, what do we get out of these? So we have 9 out of 16, which is multiplied by 15, and the result is what?
8.
Yes, well done. It is 8.4375. Right, that's correct. Okay, so yeah, you're right. Right, 2 decimal places is popular, which is approximately 8.4 units. Yes, units. Okay, so we have this. So we just had to get the LM there for 3 marks there, and we've just got it. Okay, so think about that one. All right, so we are in B now, and we continue to the next question. Next question. Next question. Here's another question. Okay, we're doing geometry because perhaps that is what was recommended for us to practice together. And we shall return with Ayanda to look at more probability, please, and Venn diagrams in our tomorrow's lesson. So yeah, I'm planning that we're going to spend a lot of time on the probability as well. But also this is very important because it is very examinable. And so it's very important that we understand this. In the diagram below, a circle with center O is drawn. Here is the circle, it has center O and it has been drawn. Right, OD is perpendicular to AC. OD is perpendicular to what? To AC. OD is perpendicular to AC. OD and AC intersected E. OD and AC intersected E. A, B, C, and D lie on the circumference of the circle. Let's see. A, B, C, and D lie on the circumference of the circle. Determine the length of BE in terms of AO and ED. Determine the length of BE in terms of AO and ED. Okay, this one is purely grade 11 work. This is purely grade 11 work. Okay, they've given us information here like OD is perpendicular to AC. Here is OD is perpendicular to AC, and it's already marked as 90 degrees here. Now, determine the length of BE in terms of AO and ED. All right, so okay. All right, so determine the length of BE, right, in terms of AO and ED. Okay, it's obvious this one, right? So I know that you can easily get this one right because you are actually people who know grade 11 work very well because it's the end of the year now. Everybody has gone through this kind of stuff. And now let's see what can be said for just 2 marks. We must find BE out of this. Okay, so but we can see clearly, looking at the diagram, that BE is equal to what? Here is BE, right? BE is equal to twice OA, the radius, minus ED. We can see that BE is equal to twice OA, the radius, minus ED. Because we can see that BE in Afrikaans, they say ampere, almost, ampere, almost. So this BE is almost the diameter, but what is it short of to reach D, this BE? It's short of this little thing here. So it means, therefore, we can just say that this BE is actually the same as twice OA, twice the radius, which means that this BE is actually the sort of the diameter, but short of something, short of ED. This is what we say. BE equals twice AO minus ED. Right. So why? Because this is a play on radii. It's a play on radii because we can see clearly at this point that BE is almost under the diameter of the circle, but it is missing ED, so it is therefore advisable to say the BE is twice the radius, but missing ED. So we have determined the length of BE in terms of AO and ED. Radii is the reason. We are done. Next question. Next question. Okay, now we need to prove this one. 4 marks. You need to prove that twice AO minus ED squared is equal to this. Right. Let's do this here. Okay. This one I can even give to you, but yeah, okay. Let's prove it together. This is an interesting, these are interesting questions, okay? What do we say about this thing we need to prove? We need to prove this statement here. But we know that if this is perpendicular, then AE is equal to EC, which is a line from center is perpendicular to chord. AE equals EC. First, we realize that AE is equal to EC, line from center is perpendicular to chord. Line from center is perpendicular to chord. Okay, next. BE squared is equal to BE squared Let's look at BE squared. What is BE squared? BE squared is equal to BC squared minus EC squared. So this one is we can use Pythagoras. We can start, if we want, we can start by saying BC squared. Normally we start with the hypotenuse. And we say then BC squared is equal to what? BC squared is equal to the sum of the squares of the other two sides, is the Pythagoras theorem. Okay, so you can say BC squared is the sum of the squares. So BC squared is equal to BE squared plus EC squared. BC squared. BC squared is equal to, okay, so BC squared is equal to BE squared. BE squared plus plus EC squared. Right, so that's what it is not what I want to say. I want to say BC squared is equal to, BC squared is BE squared plus EC squared. BE squared plus EC squared. Okay, this is Pythag. This is Pythagoras. And from Pythagoras, we're able to make some achievements. What are the achievements? The achievements are, we can make BE the subject of the equation. In here, for BE squared is equal to BC squared minus EC squared. Okay, it's just a transposition of terms. Transposition of terms. How far are we now with the proof of these? Thus, we can make the observation that if you have this side here, we need to prove twice OA minus ED squared is equal to this. So we must prove that twice AO minus ED squared. We'll put a parenthesis here. Right, putting your parenthesis here. So that this side here, we're proving that the left is equal to right. So twice AO minus ED squared is equal to what? Equal to, right, we process this together. Right, it must be equal to BC squared. Okay, so we have this. BC squared. And already have the BC squared here that is appearing. And also now we have the EC squared that is also evident there. But what have we done there in the previous question? In the previous question, we had to write that BE is equal to twice AO minus ED. So twice AO minus ED is BE. So this is equal to twice AO minus ED is BE. So we have BE squared which equals BE squared is then equal to this. Right. So it is exactly equal to BE squared is BC squared minus EC squared. What is EC? Right, they've put AE there because EC is equal to AE. Because EC is equal to AE, perpendicular from center to chord bisects the chord. So, yeah. So BC squared. So this is AE squared. Because EC is equal to AE. EC is equal to, so in the place of EC, you can put AE, so we have this. And that is the answer. That is the answer. Okay, so we've proven, therefore, that twice AO minus ED all squared is equal to BC squared minus AE squared. Okay, we have that. Next question. Okay, look at the proof. You will have a chance to watch this again. After. Yes. So you think about it. You think about it. All right. Next question. There is an easy question for us to enjoy ourselves. In the diagram below, a circle is drawn passing through A, B, C, D. A, B, C, D. Right, so we have a cyclic quad. This one is a cyclic quad. Okay, so it is a four vertex shape that whose boundaries, or rather whose vertices, happens to lie on the circumference of the circle. So what do we do? BED. BED is theta. Right, it has been shown there. It is exactly theta here. We can see. BE and ED. So we have BE and ED are tangents at B and D. So you have that these are tangents and therefore they are equal to each other. So BE and ED are tangents at B and D. B and D, you need to prove this one. Prove that angle BCD is 90 degrees plus theta over 2. Prove that one. So to prove that one, I'm going to give you, how many marks is it? 6 marks. 6 marks. So I'm going to give you 3 minutes to prove this. Okay, so you need to have a paper, a book where you write our stuff. You don't mix our stuff with other stuff. You don't mix our things, our notes with other people's notes. During our discussions, we'll have a chance to solve 1 or 2 questions. I cannot give you a million questions because I understand that you need to also do schoolwork. you have homeworks to do, you have other subjects to do. So I don't want you to break down. But I'm then saying here, I'm giving you 3 minutes to prove this result. To prove that angle BCD is 90 degrees plus theta over 2. Okay. Please let me know when you're done. Prove that BCD is equal to 90 degrees plus theta over 2. 3 minutes has been allocated for these simple proof. I gave you this as a homework. That's why I'm even giving you 3 minutes, because I know that you're not seeing this for the first time today. I gave this yesterday, but I'm interested in just seeing what you are capable of doing. Right, because I know that I gave you these. Okay, so you are still here? Right. Righty, righty, righty. Right, so we have this. Right. Right. Okay. We continue. Okay. You done, guys? Let me know, please, because I'm just giving you this so that you tell me if you're done, you finished or not. This is not there to torment you. I'm not here to torture you. I'm not here to make you feel pain, but I'm here to lift you up. I'm not here to break you down.
Yeah.
Just need to prove that BC 90 degrees plus theta over 2 because the theta is here. That's all. Right, so I'm sure that I'm sure that you can do this with your eyes closed. I'm sure that you can do this with your eyes closed. Right. You can do these with your eyes closed. Okay? Too easy, too obvious. Too obvious. Okay, I'm giving you some minutes so that you think carefully about these. And right, anyone done yet?
Not yet, sir.
All right, I'm giving you like 2 more minutes. I want to see if you can be able to prove it. I'm trying to stretch your minds because I know everything is obvious, but you must try something in class. If you're a student, it's healthy. It's like in sports. You can't just do sport when you never um like practice, try something during the training. Right. So yeah, we have that. Right. Okay.
I'm done, sir.
Did I-
Yes, sir.
Okay. How did you prove that, Marang? Just a story? What did you
Ah,
do?
sir, I didn't get it. I tried,
Yes.
but I got stuck somewhere.
All right, that's fine. Okay, because we're just practicing with these. It's not train smash. Right. After to prove this, you realize that first things first, because the examiner said that BE, right? Here is BE and here is ED are tangents at B and D respectively. So at B and D you have tangents. So if you have these tangents, what do we do with these tangents? Right. So with these tangents, what we do is we um, realize they're equal. So if they're equal, then um, we can be able to construct something here. We construct. Okay, because once we construct, we realize that we have a triangle, and this angle is going to be equal to that angle there. Right, so that construction is very, very important. Um, so we do as part of the solution, you do a construction. What is the construction? The construction is that you actually join DB, like I've just done. Normally we use a dashed line to perform a construction, but obviously one can use a solid line there. All right, so with that said, we are able to make a couple of observations based on the construction. What observations can we make? We can be able to see that angle DBE or DBE, right? So angle DBE is equal to angle BDE is equal to angle BDE, right? BDE. Right, so those angles, obviously, because this triangle here is isosceles, is isosceles triangle. So we have that these base angles are equal to each other. And if they are equal to each other, what do we then say? Right, because these are two angles, we can just say 180 degrees is the sum of the angles in the triangle. from 180 degrees, we just subtract only one angle, which is this one, and then we divide this difference by 2. It will give us exactly the size of each of these angles here. Alternatively, you can add these with that to get 180 degrees because of the sum of the interior angles of a triangle. Right. And that means at this point, we have that these two angles are equal to each other. Now, when they are equal to each other, right, why are these equal to each other? These two. Right, so they are equal to each other, these angles, because of the tangents. Tangents from same point. From same point. So the tangents from same point are equal to each other because they're drawn from the same point E. Okay, right. We have these, but these are then equal to each other. Well, if you don't want to say this, you can say that these angles are equal because BE is actually equal to DE. Okay, like that. So we continue. We continue with the proof. We continue with the proof. Right, so now with this, we have the following. We have the following. Right. Right. Right, so we have that. Okay, we're done. Right, like I said, this angle is equal to this because these two sides are equal, tangents from the same point. And therefore, this angle, you can get each one of them by saying 180 degrees is the sum of the angles in the triangle. We subtract this one, divide by 2 to get this part. And then we are just almost done with the proof. So angle C now. So what does it mean about angle A? Because we know that this angle here is 180 degrees minus theta over 2, and this is also 180 degrees minus theta over 2. So yeah, each one of these is 180 minus theta over 2, 180 minus theta over 2. And then now we can get angle A. We can be able to get angle A. What is the size of the angle A? Right, because this one is a tangent, remember? Okay, because they said these are tangents. Okay, you can use the top one, the bottom one. This is a tangent and that is a tangent. So the fact that this one is a tangent, so it means we can use the Ten-Chord theorem. Ten-Chord theorem says that if there's a tangent like this and you have a figure like this, then this is equal to this. So we have that situation. So this angle here must be equal to that angle there, which means the angle A also must be equal to this angle here, because we have the angle between a tangent to a circle and the chord equals the one in the alternate segment. So it is actually 180 degrees minus theta out of 2. All right, you get this. Right, so in other words, we come here and say thus angle A is equal to also 180 degrees minus theta out of 2. Why is angle A equal to this? Because of the 10 chord theorem. 10 chord theorem. Okay, because of the 10 chord theorem, so angle A is equal to this. Okay, if angle A is equal to this, then what is angle C? Okay, because they want BCD. This one, BCD. Opposite angles of a cyclic quad, A plus BCD, angle A plus BCD must be 180 degrees. But angle A plus angle BCD is equal to 180 degrees. Angle A plus BCD is equal to 180 degrees. Why? Because these two here are opposite angles of cyclic chords. And the opposite angles of a cyclic chord are supplementary, meaning their sum is 180 degrees. And then if we get to this point, we already have BCD here. We already have angle A, so we substitute everything here. Which means at this point, we can just substitute angle A, which is 180 degrees minus theta. So in the place of A, we have 180 degrees minus theta out of 2 plus BCD is equal to 180 degrees. So you can divide here by 180 by 2. What is 180 divided by 2? 180 divided by 2 is actually equal to 90 degrees. Okay, so that is equal to 90 degrees. Right. 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 So you have therefore now this one 180 divided by 2 is what? Is 90. Right. So if you have 180 divided by 2 is actually 90 degrees minus theta out of 2 plus BCD is equal to 180 degrees, which means BCD is equal to, so you transpose everything, is 180 degrees, and then you subtract 90 degrees, and then you add the theta out of 2, which means BCD is equal to, what is 180 minus 90? It's 90 degrees plus theta out of 2. And it's exactly what we're to prove here, because we're to prove that BCD is equal to 90 degrees plus theta out of 2. And we've proven that BCD is equal to 90 degrees plus theta out of 2. And we've proven that, and we are done. Okay. So, we continue. We have proven that one. It's very easy, and it was given to the IB students in the year 2017 November. We continue. We have also another question that was given to the IB students in the same year. They decided to give them a diagram like this, and they said, in the diagram below, 3 equal circles of radius 3 units. So there's a circle here, and this circle here has a radius. The radius is actually the distance from the center to the boundary, and it is 3 units. And also you have, each one of them has also, even this one here is 3 units. And also this one here is also having a radius of 3 units. So these are congruent circles, congruent circles, congruent circles. Okay, we have this picture. And also, yeah, all right, you have that kind of a situation. Right, so in the diagram below, 3 equal circles of radius 3 units are positioned so that they touch each other. If they touch each other, okay, they touch each other, and the diagram is clear. Right, BT is a vertical common tangent. This BT is vertical, we can see, but it's a common tangent because it is a tangent to both circles at the bottom. Right. And CD is a horizontal common tangent. CD is horizontal, but it's a common tangent to the circles at the bottom. Right, to the same circles. Okay, this one is vertical and it is a vertical tangent. This one is a horizontal tangent. Okay. So that the length of BT, so we must find the length of BT, so that the length of BT is equal to this. 3 the square root of 3 plus 6. Okay, so this one is very, very easy. I must give it to you for a good, how many marks was it? 5 marks. So I can give you like 3 minutes. If I give you 3 minutes, because it's just 1 second, so I want to see what you can do, please show that the distance from B to T is this. In 3 minutes, then we shall do the corrections. Let me know what you find. And then you'll tell me what you did to solve this. If you get this answer. All right, let me know when you're done, please. It's just a small little exercise. I don't want you to sleep. You must work alongside. We must work together. So You done, everyone? Not yet. Okay, I'm just testing you. I'm just testing you to see, because we shall do these warm-ups. Please, now we need more than 2 lessons in a week. If need be, we alternate the days. We meet today, we don't meet tomorrow. We meet today, we don't meet tomorrow. We meet today, we don't meet tomorrow. If you get what I mean. We need to get to that level of seriousness, of really saying we cannot meet twice a week. It's not enough. We must do extraordinary things. I know this is very obvious. Okay. You done, folks? Not yet. Right. Okay. So you have to do constructions. You need to join these ones here. And then you need to join these here. Like that. But this one is a radius is 3, and that is 3. This one is also a radius from the center to the circumference is 3. From the center to circumference is also radius 3. So it means, therefore, this one is 6, 6, 6. Like that. So what is all this? So you have this. So you have a circle, you have a triangle like this. Okay, if this is drawn like this is a tangent. So a tangent and radius are perpendicular to each other. So this one is 6, and this one here is 3. Then we're able to find what we can call the height of this triangle. Yes. So if you call this one h, you can realize therefore that h squared is equal to what? Okay. You can start as follows. You can start by saying, okay, you already know that x squared plus y squared is equal to r squared, and this is Pythagoras. This is Pythagoras. So the hypotenuse is 6. The adjacent side x is 3. The height is h, like y, vertical axis. So we're able to see that h is the same as this is squared. So 6 squared is 36. The 3 squared is a 9. And therefore, if you subtract 36 and a 9, you get a 20 what? You get a 27. You get a 27. So you have h now. What is h? So you are able to see that h is the same as the... So if you have h squared is 27, what is the meaning of this? So you have h squared is 27, you take the square root, you take the square root. So h is, this is 9 times 3. What is 9 times 3? So this is the square root of 9, the square root of 3. What is the square root of 9? Square root of 9 is 3. So this is 3, the square root of 3. Okay. So now we got this. Or it means that this h here is 3, the square root of 3. Now this one is 3, the square root of 3, but you want to find bt. So to find BT has a 3 here, but also the distance from here to there, what is this distance? Is the same as the distance from here to there, which is 3. The distance from here to there, which is 3, is a radius. From the center to the circumference, the radius, each of these circles are actually all of radius 3. So which means this is 3 units, and that is 3 units. But the height is actually h, which is this, and therefore we conclude as follows, right? So we want to therefore find BT, hence BT is equal to the height h plus 3 plus 3, which is BT. What is the height h? Is 3 the square root of 3 plus this one, which is 6. So which means BT is 3 the square root of 3 plus 6, and we have proven that one. Okay, so it was a very simple proof for us to do. Right, so we have just done this one. Right, and now the time is just after 8:30. It's like 8:39. So we are actually obviously just 2 hours and a few minutes into our discussion. So what I'll do is I will give a homework, and I'm gonna save the video and send the video in a couple of minutes. What you do with a video like this? You write down the notes. How do you write down notes? You need to make time. Make time when you are free. You sit down for 2 hours. You can fast forward the video, you know already what's happening. You can push it forward just to get the question, get the answer, get the question, get the answer, and then write the question, the answer in your book. Why do you have to copy down the question and the answer in your book? Because now when you have them in your book, then you can close them, and then you can study the things in your book, and then you have your book, you close your book. When you close your book, you copy the question down on paper. After you've copied it on paper, you see if you can be able to do the question without looking at the answer. Okay, you try to see if you can do the question without looking at the answer. Then it means if you can do it, kudos to you. If not, you need to practice a little bit more. Okay, so we have been able to do this question 12 from the IB exam. Okay, there it is. They said we'd show that BT is 3 the square root of 3 plus 6, and we have just done that. This was 2017. Okay, now they've given you some more questions like this. And you need to do more of this. And this was the end of the exam in 2017. Right, so I'm going to send you another homework. Okay, this was A, and this now it's B. Maybe we can just practice with this one quickly. 3 identically sized cylinders are stacked on top of each other, is shown in the diagram below. Okay, identically sized cylinders, here the cylinders, they're stacked on top of each other. Right, they are anchored down by a piece of rope from A to B. Piece of rope from A to B. There's just some rope from A to B that anchors them. That's right, like supports them. Right. A, C, D, and E lie on the same horizontal plane. A, there. C, D, and E lie. No, we have A, C, D, and E lie on the same horizontal plane. Right, B, C, and D lie on the same vertical plane. B, C, and D. Right, so you have B, C, and D lie on the same vertical plane. Right, so B is the highest point on the cylinder. Right, so here is B is the highest point. You can see B is the highest point. Okay, we're finishing, guys. The angle of elevation from A to B is 50 degrees. The angle of elevation from A to B is 50 degrees. Here is the angle of elevation is 50 degrees here. Okay. BEA is 70 degrees. BEA is 70 degrees there. Okay. The radius of each cylinder is 3 meters. Okay, is the question. So the radius of each cylinder, okay, each cylinder, the radius is the distance from the center to the circumference, and it's like 3 meters. Okay. Calculate the length of AB. The rope required to anchor the cylinder down. Want to find the length of AB. What is AB? Okay, so you have this one. I'm sure that you can do this one with ease. Very, very easy. Very, very easy. Right. We need A, B. How do we find A, B? Right, so the couple of things obviously you need to remember here, because this question is very similar to what we just did right now. And so at this point, there are a couple of things you can actually try to obviously consider here. And what can we try to consider at this point? We have learned a couple of things, and this is exactly the thing we have learned. And now, what do? We can be able to find, for instance, the sine of 50 degrees. Right, we learned that we had this situation of these stacked up, so we could therefore be in a position to find exactly the height here. Right, and if these things are on the same horizontal plane, there this is at ground level. We actually have been able to find this one here. Like, it was like BT, and we saw that the BT was 3, the square root of 3 plus 6. So BT would be the same as what? Okay, I'm gonna just quickly do it there so that we are able to get that one. So you have 3, the square root of 3, you add 6 for the answer. It means that BT is approximately 11.19615. Okay, that is BT. So now we want to find AB. Okay, if these things are on at ground level, right, you are able to obviously understand what is happening here. And now we have the length of AB. Right, so you have a triangle that way. So if you have a triangle and you bisect like this, it would mean that it is this is perpendicular here, and these are actually ground level. So you can see that the sine of 50 degrees in view of SOHCAHTOA, it is the opposite side of 50. It's the opposite 50, which is actually, we called that BT, or sort of the yeah, we called it BT, if you like, divided by the hypotenuse, which is AB. Okay, so the sine of the 50 degrees is like the BT. These are at ground level, so it's actually the opposite, the 50 over the hypotenuse. And then what is this here? The sine of 50 degrees is BT. What is BT? It is 11 point, you can call it 11.2. From this BT, you can call it 11.2 over AB, which means AB is equal to 11.2 over the sine of 50 degrees. What is this here? It is actually 14,62 meters. 14,62 meters. That is the length of AB. Think about it, but these things are at ground level. I know the diagram doesn't look, it's a 3D diagram, so it's a three-dimensional diagram there, but yeah, note that here. Okay. The next question. Okay, this was the end of the matric paper. It was uh, the end of the paper on geometry. Right, so you can see the marks at the end are actually 115, the total for the paper. Right, so, right, if the second rope EB has a length of 13 meters, second rope EB has the length of 13 meters. Okay, if that is actually 13 meters, right? So there are two ways to spell meters. Either you can say 13 meters like that, or obviously the British is 13 meters. You can change that. Right. Then determine the straight line distance between E and A. Determine the straight line distance between B and A. You see? Between E and A. You need a straight line distance between E and A. Okay, so you have this. Okay, you already have this one here. What is this one here? We have found AB already. So we have this kind of a diagram. Right. You have, you get the labels right. We have EA at the bottom and you have B at the top. EA at the bottom. Right, you have EA at the bottom and you have B at the top. Right, you already have a couple of things. You already have 50 degrees and 70, 50, 70 at the bottom. You already have 50. And you have 70. Okay, if you have already two angles, then you can get the third one at the top. Okay, this one you already know is 13. This one you already know AB. We got AB to be 14,62. And we just need this one here. So it's an obvious way to get this one. So you can use any of the rules that we already know at this point because this is very, very obvious. So we want to find EA. How do we find EA at this point? Obviously, we need to find the size of the angle B. What is the size of the angle B? Right. So, to find the size of the angle B, okay, right. I want us to look at this very carefully and remove this angle here. And remove this angle here. But obviously note that we have this one is 70 degrees at the angle E. Right. Obviously I marked this here. But now if you understand that this angle is sort of on the other side, and the 70 is here, and then now we we will be interested in finding the size of the angle B. Right, how do we find the size of the angle B? So we can work in the triangle, obviously, and say the following. Right, so I'm just gonna bring my pen, and this is the last question we shall do, and then you can rest. Right, you can do other things, other subjects as well. Right, so you have want to find the angle B. So the sine of the angle, you can find we need to find A first for us to get B. So we shall say the sine of A divided by 13. The sine of A, right, divided by 13 is equal to the sine of 70 divided by 14,62, which means the sine of A is the sine of 70, 13 sine divided by 14,62. So which means A is the sine of this one, sine 70, 13 divided by 14,62, which is this. The angle A becomes, if you use a calculator here, you get 56,68 degrees. So this one is 56,68 degrees, in which case, therefore, we just need to find B. Right, the sum of the interior angles of a triangle. So the angle B is the same as, there's no this. The angle B is the same as what? Right, the angle B is the same as 53,32 degrees. So the angle B is the same as 53,32 degrees. Or we have this. Now then we have to find EA, because we already know that this one is 53,32 degrees. So which means that we can find EA as follows. Hence we have EA over, by the sine rule, over the sine of 53,32 degrees is equal to, okay, I know that you're thinking too much and you might be sleepy already. So it's EA over the sine of this is equal to, you can take this one or any of the sides. So you can take 14,62, you divide by the sine of 70 degrees. Right, without wasting time, we cross multiply and use our calculator, and EA becomes 12,48 meters. And therefore, this is the answer to the question. So at this point, what did they ask us to do? They said that if the rope that determine the straight line distance between E and A, so EA is this one, and we are done. And that is the answer, and we are done. And we are done. Okay. So this was the last exam question in this exam out of 150 marks. So I must thank you guys for joining us. I will send you the homework in the next couple of minutes on geometry, circle geometry. I'm gonna look for past exam questions, and then we shall talk on WhatsApp. But we need to meet this weekend. Everybody, we need to meet this weekend. But you need to decide on the time that is going to suit you. On Saturday, that is going to suit you. On Sunday. This today is what? Is the 20th. We are literally left with about 10 days before the exams begin full power. So we can't do routine. We can't just do 2 meetings per week. It's our last week that we have now left. It's like 10 days, 20th through 30th. So think about it, but need to find time, even if we meet at 12 o'clock midnight, 12 o'clock midnight to 2 a.m., 2 hours, something like that. Okay, thank you guys. We'll talk on WhatsApp. Goodbye. Goodbye, guys.
Bye, sir.
Okay, bye, Marang.